So what I'm going to talk about today is trying to understand the neural circuits that may contribute to the development of emotion regulation and mood pathology, with a particular focus on trying to start in the school age period to understand what kinds of functions, or even earlier, maybe in the preschool period, the neural circuitry and what sorts of functions are going to predict those children who may be at risk for the development of mood pathology as we move into the adolescent period, where we know there is this increased risk. And most of you probably know that depression is a very devastating illness. It has a high lifetime prevalence, a scarily high lifetime prevalence, and a very large personal and societal burden. Our current treatments are frequently inadequate or ineffective. Many folks don't respond or will still relapse after. And this is a kind of a form of pathology that we know can start as young as preschool. It has prevalence that rises, but some of the precursors or markers are clearly present very early on in life, and those might provide avenues or windows into potential pathways for early intervention or prevention. There is now, I think, a nice body of foundational work in adults with depression that have identified particular psychological and neurobiological deficits that may contribute to depression, but there's really relatively little work on neurobiological risk factors in children or in adolescents, and so that's where we have been focusing. And in trying to understand this, I and my colleagues have been working off of admittedly simplified model of what might be some of the mechanisms that contribute to the development of mood pathology or affective pathology. And we know that this is, there we go, that's the right button. We know that there are obviously genetic mechanisms and a host of psychosocial mechanisms that have an important role. Yesterday, we heard Terry Jernigan give a lovely talk talking about understanding how genetics set the stage for the impact of environmental factors, and we know that that's an important set of interactions in relationship to mood pathology. But we also think that these factors are influencing particular neural systems that support particular dimensions of behavior that are likely to be relevant. And today, I'm going to focus on, in particular, reactivity to negative emotional stimuli to regulate or reappraise that information. I'm sure I know others are in this audience are working on looking at things like reward responsivity and how that interacts, but I'm going to focus here today. And I'm going to focus on these neural systems, in particular, the amygdala and the hippocampus, as well as prefrontal systems. So negative emotion reactivity is, again, a kind of a broad construct. And we know that the amygdala and regions associated with the amygdala are critical for how we respond to salient events in our environment. The amygdala isn't responsible just for responding to negative events, but to salient events more generally, and this can be both positive and negative, and it's going to be in part determined by what that individual finds as salient. And there's very consistent evidence now in the adult literature, at least, that you get increased amygdala reactivity to negative emotional stimuli in individuals with depression and in those at risk for depression but who don't yet have the illness. And we know that the amygdala is really functioning as part of a larger network of regions that are involved in aspects of emotional processing and emotional experience, and that includes the hippocampus and other medial temporal lobe regions. The hippocampus, we've known for quite some time, is obviously critical for the reaction to negative stimuli. It plays a critical role in helping to modulate the stress response. We know that hippocampal volumes are altered by adversity and stress, and we know that there are cellular and synaptic mechanisms that are responsible for this from the animal literature. And we know that hippocampal volume is reduced in depression, again, potentially related to stress and chronicity. When people have kind of an enhanced reactivity to negative emotional stimuli, the ability to regulate those responses becomes particularly critical. And we know that emotion regulation impairments are part of the pathology associated with depression as well. And importantly, the general systems involved in cognitive control are just as critical for emotion regulation as they are for sort of non-emotional aspects of control. And we know that in depression, you see altered activity of emotion regulation regions. We see that, both in adults and in adolescents with depression. And I also want to highlight the potential role of the anterior insula, which hasn't received, I think, as much attention in the emotion regulation literature. The insula is an interesting region, the anterior insula in particular, because we know it's important for the experience of emotion and interoceptive awareness, but it's also thought to be this important way station that helps to integrate sort of top-down control signals with this bottom-up information coming from sensory systems and receptive systems. And we know anterior insular volume and activity is reduced in depression, and even more importantly, we know that individual differences in anterior insular volume predict the recurrence of depression in children who've already had a depressive episode. So it may also play a critical role in emotion regulation impairments and depression. So the goals of the work I'm going to present today was to take data from a large longitudinal sample of children that had been followed from the early preschool period, started by my colleague Joan Luby, and to look at both brain function and brain structure as predictors in children with no history of psychopathology, look at it as predictors of changes in emotion regulation and depression over time. So in particular, we focused on activity and what we're going to refer to as an emotion reactivity network, and I'll show you in more detail what we mean by that, to test the hypothesis that greater responsivity of regions in this emotion reactivity network to things like sad faces in a network that includes amygdala, hippocampus, and other medial temporal regions, that it predicts depression and poor sadness emotion regulation skills, both at baseline, and predicts a worsening of these outcomes over time. We also looked at a network of brain regions involved in emotion regulation and tested the hypothesis that less activity, less engagement of these regions to sad faces would predict worse depression and worse emotion regulation skills, both at baseline and over time. And then in addition, we also looked at brain structure, in particular amygdala, hippocampus, and the anterior insula, to test the hypothesis that smaller volumes in these regions would also predict depression and worse emotion regulation. So as I said, this was children from a longitudinal study that's been going on since these kids were in preschool. We took only those children who had no previous history of psychopathology. So this might actually be a little bit of an extra clean sample because they have been followed prospectively over time. And so if they already developed some form of childhood psychopathology, we didn't include them in this particular study. We had 60 kids at baseline, and 48 of those we were able to follow up approximately 18 months later. They were a little bit, on average, less than 10 at the baseline scan and just a little bit over 11 here. Pretty equal males and females, very diverse sample in terms of ethnicity and socioeconomic status. And I just wanted to point out, kind of to give you a sense of where these kids were, this is scores on a measure called the Child Depression Inventory. There are T-scores. A clinical range is going to be above 65. So at baseline, these were not very depressed kids, but as we moved into the follow-up, we started to get more children who were showing increased rates of depression. And this is to some extent what we'd expect from the developmental literature previously about sort of an increase in depression rates as you move into adolescence. And again, I wanted to just highlight Joan Luby because she really started this study. For the functional imaging part, we used a gender judgment task of emotional faces. We chose this task because there had been some previous literature suggesting that amygdala reactivity biases and depression came out more clearly when you used a task that did not orient people to focus on the emotional content of the stimuli. So we did a gender judgment task with the idea that that would give kind of more room for biases to come out. We used faces from the MacArthur Network face stimulus set, and we used multiple different kinds of faces. We had sad and neutral faces, and for the sad faces, we had both full intensity and then morphed intensity or half. Ooh, gosh, sorry, I'm a little too excited with that. Okay, there we go. For this particular set of data analyses I'm going to show you, we averaged the full intensity and the half intensity faces, but you don't see a different result if you look at them separately. And let me just say a bit about the opioid networks, and I highlight Catherine Luking here because these were networks that she identified in an earlier study looking at functional connectivity of the amygdala. So we focused on an emotion regulation network, which were a set of regions in prefrontal cortex and parietal cortex that show negative correlations with resting state activity in the amygdala. And this is a set of regions that others have argued represent sort of control over emotion processing in the amygdala, and that this anti-correlation or negative correlation is what you would normally expect. And then also an emotion reactivity network that included the amygdala in yellow here, and then hippocampus and other medial temporal regions. For structural imaging, we did high resolution T1 imaging. We segmented the brains using FreeSurfer and used the Desikin-Kalani atlas to pull out bilateral amygdala volumes, hippocampal volumes, and anterior insula volumes. And all the analyses I'll show you here control for whole brain volume to try to get at whether this is an effect specific to these brain regions or something that's more generally characteristic of volume changes overall. And then self-report measures, we focused on the children's depression inventory on the day of scanning, and then a well-validated measure called the Children's Emotion Management Scale, which is a self-report measure of how well children are able to cope with feelings of sadness. And they did a very extensive diagnostic interview as well that I won't focus on today that ruled out previous psychopathology. Okay. So what I'm going to do is show you the data, first focusing on the baseline or the cross-sectional relationships, and then showing you how the brain measures at baseline predict changes in function and self-reports over time. So just as a reminder, the measures we had volumes of the amygdala, the hippocampus, and the anterior insula, and then we had activity in the emotion reactivity network, which was amygdala and hippocampus, and activity in the emotion regulation network. And so let me start by focusing on the emotion regulation reports. And what we found was that at baseline, we see a negative relationship between amygdala volume and emotion regulation skills, such that greater amygdala volume is associated with reduced emotion regulation. Now, I would say that's not initially what we predicted, but that actually does fit with some of the literature suggesting that you get amygdala hypertrophy associated with stress or negative events in the environment. But truth in advertising, it wasn't what we initially predicted. However, we had predicted that we would see this positive relationship between anterior insula volume and emotion regulation, so greater anterior insula volumes associated with better self-reports of emotion regulation. And we also saw the predicted relationship with activity in the emotion reactivity network, so greater activity in the sad faces was associated with worse self-reports of emotion regulation. We didn't see a relationship with hippocampal volume or emotion regulation activity in this baseline relationship. When we then looked at how these baseline brain measures predicted behavior over time, what we found was that insula volume indeed predicted not only baseline self-reports of emotion regulation, but the self-reports at follow-up. And we saw that was also true for activity in the emotion reactivity network. And more importantly, at least for the anterior insula, when you controlled for baseline emotion regulation, anterior insula volumes predicted change or improvements in emotion regulation self-reports over time. This was only trend level for the emotion reactivity. It was like 0.09. So this suggests that anterior insula volume is predicting not only concurrent self-reports of emotion regulation, but the likelihood that you're going to see improved emotion regulation over time. And just to illustrate the magnitude of the relationship, these are residualized scores here controlling for baseline, and you see this positive relationship, and I should point out that it holds even if you get rid of this little guy here, which was a bit of an outlier. In terms of depression, I'll show you the data in the same way. Here we do see that hippocampal volume shows the predicted relationship between concurrent depression reports with greater volume associated with reduced depression. We also see that, again, activity in this emotion reactivity network predicts depression, so greater reactivity to sad faces, more depression, even in these beautifully healthy kids. And in terms of follow-up, we see, again, that hippocampal volume predicts not only baseline, but also over time. Although in this case, when you control for baseline depression reports, you don't see this relationship as a function of change. So it suggests that that relationship is there at baseline and continues over time, but not necessarily predicting change. So to summarize and conclude, we did find that activity in these emotion reactivity regions predicted emotion regulation skills and depression at both baseline and follow-up. We found that amygdala volume predicted emotion regulation skills and hippocampal volume predicted depression. Perhaps most importantly, we found that these anterior insula volumes predicted both emotion regulation skills at baseline as well as follow-up, but also improvements in emotion regulation over time. We think that these kind of data start to identify functional and structural predictors of function in children, even with no psychiatric history. That might be a clue as to the neural circuits that are contributing to risk or resilience for depression onset in adolescence. We think that they may be potential markers of risk for depression. And we're going to need to do continued longitudinal follow-ups to look at several different things. We are now finishing up data processing for the brain data at a second and then a third wave of follow-ups in these same kids, so we can look not only at how baseline brain measures predict function over time, but how trajectories of change in brain structure and brain function predict trajectories of change and function over time. We think that this will give us a better clue about how these things are predicting the emergence of depression over time as potential targets for interventions. An important question we'd like to ask is the degree to which these neural measures predict important function over time, over and above behavioral measures, partly for practical reasons, but also for theoretical reasons to try to understand those relationships. So I'll stop there. Thank you. So I think we have time for questions. Be nice, Sonia.
I love that you're coming into the child development space because your thinking is so clear. Thanks so much. I was wondering if you had a chance to get measures of episodic memory, given its important relationship with hippocampus development.
It would be great. We have one of them, unfortunately. Actually, I take that back. We did, Joan, who started the study, did the CDLT at one of the earlier waves. We haven't looked at that in relationship to this, and it's not at every wave, but we could go back and look at that, because, I mean, it's a measure. Yeah.
I found the insula findings really interesting, but I was just wondering, of course, whether you had looked at whether these insular results were more attributable to differences in the surface area of the insula or the thickness of both.
Right. So we have a previous paper in I didn't look at that in this sample. We had a previous paper in the clinical kids that looked at anterior insular volume as a predictor of reemergence of depression. And there we did look at surface area and thickness as well. And we didn't see a differential relationship. It was stronger we've mostly found it stronger for thickness than surface area in most of the studies that we've done. But honestly, in that study, the volume overall was much better than looking at either of them individually. So I think that's a great question. I don't know if that reflects a lack of sensitivity in our methods to be able to distinguish between the surface area and thickness. But most of the time when we do go break it down, it's either pretty similar or stronger for the thickness than the surface area measures.
One thought, I wanted to speculate a bit more about your ideas functionally about the anterior insula, and whether you think it's the feeling-based, modulating, top-down, and sensations of the emotion.
That's a great question. So what's driving that? Is it the role that the insula plays in the regulation piece of things or the emotional experience piece of things? That's a great question. I think the paradigms that we use in the scanner currently are not great for teasing that apart because they don't really require any regulation, so we can't look at whether the activity in the insula is being more driven by the sort of regulation demands versus the emotional experience demands. So as these kids are moving into adolescence, we're planning for a next phase, and the plan is to actually switch to doing a task that's probably developmentally more appropriate and will let us get more at, is it the regulation piece or is it or both of those? So it's a great question. I don't think we know yet. Margaret, do you have a question?
It seemed like your emotion reactivity areas predicted emotion regulation really well, but that your emotion regulation areas didn't. And I was wondering if you could talk a little bit about why.
The bane of my existence. Again, I think this does, my hypothesis is that it relates to the task we use. So this task was not designed as an emotion regulation task. We started the study when a lot of the kids were 7, 8 years old, so we wanted to use a task that was going to be pretty easy for them to do. So it's very possible that this is just not a sensitive way of eliciting activity in the emotion regulation network. One of our other colleagues, Amy Belden, who's not here today, has piloted a child-friendly, explicit emotion regulation paradigm that he's run in a small subset of these kids. There we see much clearer regulation of these emotion regulation networks, and they clearly predict individual differences in depression. So we're going to move to using that paradigm as the kids move into adolescence to try to get at this. Thank you.